Hi everyone, welcome back. So we're going to be talking today about the meaning of p-values, which is something that's come up already in our discussion of null hypothesis significance testing. We're going to go into a little bit more detail here because it's used in other contexts besides just in hypothesis testing. P-values are a fundamental tool in assessing experimental results. They are basically one of the underlying statistical foundations for a lot of analysis of science. They're a way of evaluating whether an observation is significant or not. But what exactly we mean by significant can be a little bit subtle, and so it's important to have a really firm grasp of what exactly the definition is and what its implications are. So here we have the definition. A p-value of an observation, so this is something that's associated with a particular observation. The p-value of that observation is defined as the probability that the thing that has been observed will occur, or that something even more extreme would occur. So this is pretty context dependent. So it's the probability that that thing or something more extreme would occur by chance. In the context of hypothesis testing, this meant that the p-value was defined as the probability of the thing observed or something even more extreme occurring, assuming that the null hypothesis is true. These are basically the same thing. In most situations, the null hypothesis is that nothing special is going on, so that the results you're observing are just chance. So, again, the probability that the thing observed would happen by chance. If it happens by chance, we shouldn't consider it significant, right? Because it's meaningless. It's just a thing that happened randomly. So we don't want to assign significance to things that have a p-value that's high, a high probability of occurring by chance. Instead, we want to assign significance to things that have low p-values. Okay, so how are we going to use this thing? If the p-value is high, then there's a high probability that it occurred by chance. So it's not hard to believe that it happened by chance, and so it should not be considered significant, right? Not significant. If the p-value is low enough, however, then it's unlikely that this thing happened by chance. So the results must be significant in some way, and we call things with a low enough p-value statistically significant. How low is low enough? Well, as a baseline, across most disciplines of science and social science and anything else that uses p-values, the standard for statistical significance is 0.05, or 5%. If your observation is less than 5% likely to occur by chance, then it's considered statistically significant. That's a pretty universal standard. It's not 100% universal. There are some areas where a higher number, so 0.1, for example, 10%, is used. This means that things that are more likely to be chance are accepted as statistically significant. So although it's a higher number, it's a lower standard of proof. But in some cases, if it's different than 0.05, then it might be lower, like 0.01, meaning that fewer things would be considered significant. Something would have to be only a 1% or less chance of occurring by chance to be considered significant. But nonetheless, this 0.05, 5%, that is the nearly universal standard for what the p-value has to be. It should be lower than that in order to be considered significant. So you will see things like p less than 0.05, right? Or maybe even less than some even smaller number. Okay, so why do we want to use p-values? What's the point? Well, the use of p-values for quantifying significance of scientific results is very widespread. Significance, got a little misspelling going on there. Most results cannot be published without a p-value less than 0.05. There are some good things to say about this, a lot of good things to say about this, actually. So the main thing is that this is accounting for chance. It's really important to consider when you observe something that it might have been caused by nothing. It might just be a thing that happened that you should not give meaning to. And so the p-value is a way of quantifying that chance, the probability that you might be observing something that is not significant. So it's important to take these the randomness of the world around us into account. We don't want to give a lot of meaning to random events or any meaning to random events, or we will find that we are very often badly wrong about things. Also, having this p-value standard improves experimental design because people who are running experiments know that they have to get over this barrier, which means they have to design experiments in such a way that you can actually calculate the p-value for the things that you're observing. So it leads to standardization and it leads to much more rigorous testing being done. But you have to be more careful about how you set up your experiments if you have to be sure that it's not chance. It means you have to build in mechanisms that will allow you to tell the difference between the things that you're trying to see and chance. Another great thing about p-values is standardization. It's that we have a standard across disciplines, across journals, across labs, across everything for what it takes to be considered statistically significant. So this adds a layer of objectivity. We can't have individual scientists or individual people arguing that their results are significant without meeting this standard. So we don't have different people trying to convince us that on the basis of different standards. And another thing that's good about it is that it is conservative, small c conservative, meaning that because the p-value standard of 0.05 is relatively low, that means that we don't very often accept random events. So this is good. So this tends to preserve the current understanding. It tends to prevent us from swinging back and forth on different opinions about what's going on in science just based on random observations. Right? So it keeps things moving in the right direction. But if there is a real effect, then it will we can design experiments that will get below this boundary, which will let us know that something real and different is happening that has to be taken account of. Okay, so there are, however, some problems with p-values. As beneficial as they are, we have to be aware of some of the drawbacks. So one of the important ones is, like I was saying at the beginning, it's about the definition. Statistically significant is often taken to mean true or real, and that's not what it means at all, right? Remember, statistically significant meant a p-value less than 0.05, which in turn means that the probability that this observation or something more extreme would have happened by chance is less than 5%. That's not the same thing as saying there's really something happening here, or the thing that I think is true is really true, or my alternate explanation is true. So it's quite different. It's a suggestion. It's a thing that you can think about that indicates this is something worth studying more, but it's not the same as this is definitive proof. It can never be definitive. So another thing to keep in mind is that chance is not eliminated. You're taking account of chance and the role that it might play in your results, and you're trying to interpret it and make sure that your thing that you have observed is not just caused by chance. But truly random events will sometimes be classified as statistically significant. This is basically baked into the definition, right? Since the definition says that something will be significant, considered statistically significant if the probability of it happening by chance is less than 5%, then that means that 5% of the time, truly random things will match that standard. We'll have a p-value less than 0.05. That's what it means. So you can never get full proof out of this. You only get something suggestive. So it's always worth following up again and again and trying different ways of testing to get at whether you think something is a really believable effect. A third problem is, of course, that these are based on probability, and probability is kind of challenging. The mathematics of probability can be quite confusing. It's subtle and challenging. So because p-value calculations require taking all of the various aspects of probability into account, it's not too hard to make a mistake. So unintentionally, errors can sometimes occur just on the mathematics side of things. And finally, p-values are open to interpretation. They are open to manipulation. And if you understand the way these things work, you can, if you are unscrupulous in your research, you can manipulate p-values. Sometimes people do this on purpose. Sometimes they're fraudulent. And sometimes they do it unintentionally. They're trying to find a result, but they don't realize how the way that they're going about it will actually change the statistics or the probability of the thing that they're looking at. So manipulation. Let's take a look at that. One kind of manipulation is what's called p-hacking. So p-hacking is a kind of selective reporting. If you run a lot of experiments, some of the individual results will have p less than 0.05 just by chance. Again, that's the way the definition works. You can't avoid that. If you take a look at the big picture of all of the experiments you run, you won't be at all surprised to see some of the results with p less than 0.05. And on the whole, nothing significant will have been seen. But if you only report the things that happen in that narrow set of experiments that by chance have gotten the p-value less than 0.05, then present them to other people who don't know about all of the other context, then suddenly these completely random results will seem as if they're significant. That's one of the ways that p-hacking can work. So I have an example of this to let you see how it goes. I did an experiment with a random number generator. I did an experiment as if I had been flipping a coin 5 times, many times. So this is 40 different experiments of flipping a coin 5 times and writing down a 1 for each head and a 0 for each tail. So for example, this is one experiment. It has 2 heads and 3 tails, right? And I did this a bunch of times. Now, if you look at the entire collection here of all of these experiments, I think you'd be pretty convinced that it's random. There's not a lot going on, that this coin is probably fair. It doesn't seem to be more or less likely to go heads or tails if you take a look at it. However, what if I only showed you part of the data? What if I came down here and I only showed you this experiment? If I showed you only that experiment, saying, hey, I got this coin and I flipped it 5 times and I got 5 heads in a row, or 5 tails in a row, as this one was, then you might think, oh, well, that's some pretty good evidence that it's a biased coin. Maybe I even show you 3 experiments. Maybe instead of saying, just showing you that one, maybe instead I show you 3 experiments in a row. These guys. Right? If I show you those, you can say, oh, well, this guy flipped this coin 5 times, 3 times. Once he got 1 head, once he got 0 heads, and once he got 2. This doesn't seem like the kind of coin that goes up heads very often. So you might be led to a conclusion that there's a statistically significant chance that this coin is biased toward tails. That's false. This is a fair coin. But by narrowly looking at this one experiment, or this one subset of the experiments, out of all of the things that have been done, you can make it look like something significant has happened where there's no significance to be found. Similarly, I could even get the opposite result by showing this experiment where it was all heads. That's going to happen pretty often if you do enough experiments. You're going to see all heads coming up. Or if I showed you these 3 experiments, then again, you might think this is a coin that is biased towards heads. That's one of the ways that p-hacking can work, by looking only at a subset of your data and ascribing significance to it. And these results, like in the red or in the blue, would be significant if it was the only thing that had happened, right? If I only flipped the coin 15 times and I got these results, then I would have a significant result and it would require further study. But in the context of all of these experiments that I've run, it's not at all surprising that I would find groups that look like this. And that's exactly how I did this. I just did a bunch of experiments and then went looking for something that in isolation would look unusual. So you have to be careful about that kind of thing. And in fact, this can happen on a grander scale without anybody doing anything wrong, due to what we call publication bias. So imagine a similar setup where each of those experiments that I ran back here, so there are 40 of them, imagine that instead of me running them and looking through them, instead, it had been 40 individual scientists who had run the experiments. They all run the different experiment where there's looking for a phenomenon that doesn't actually exist. Most of them will get results that are not statistically significant. They have a p-value greater than 0.05. And those scientists will be a bit disappointed, but they won't publish their results, and that's fine. They shouldn't. It's not a real result. But then, purely by chance, one of the scientists may get a result with p less than 0.05. So we got our one scientist who did this experiment and got this result. They, for all they know, they have a statistically significant result. P is less than 0.05. They go off and they get their thing published. right? But if we knew the broader view of all the other experimenters who had done the experiment and got not significant things, we would know to discount that particular result as probably chance. But it can be quite hard to do that, right? Because think, you had your 40 scientists all running experiments, only one of them got published. It was the one that got this random p-value less than 0.05, and all the other ones didn't get published. So as a reader, you would only know about this result that is in fact false. So yikes, right? And it can be quite hard to undo this kind of thing once it's been done for a couple of reasons. So one is that even if you tried to repeat the experiment, if you got a negative result saying, oh, there's nothing significant here, it would be hard to publish because who publishes negative results? So if you did try to repeat it, if you didn't find an effect, you wouldn't get published because, it's a negative result. People aren't interested in those. But if you did find an effect, you probably also wouldn't get published because somebody's already published about that thing. Why do we need another paper that says the same thing? So there's a disincentive to follow up. And in fact, this became a very big story in the field of psychology in recent years. It's what's called, let's write this one down, it's what's called the replication crisis. They finally went back and looked at some of the classical results in psychology to see if they could be reproduced. And they found that many of the published results that people believed were real about the way that humans behave couldn't be reproduced. There was no evidence for them when you went back and tried to do it again. That's not good. That is not good at all. So one possible solution to this is to get a central database. So basically make a registry. That's a better word for this. A registry where all experiments that are proposed to be conducted have to be registered. The results of the experiment would have to then be registered, whether they're successful or not. So it's not publication, it's just, did you do this experiment and what were the results? And then no experiments that are not pre-registered could be published. So what's the point of this? The point is that this gives the broader scientific community the context. We see how many times this experiment has been tried, and then we can see how often it's successful. And if that's, just looks like it's only being by chance because it's been tried so many times and it was successful every once in a while randomly, then we know not to put a lot of credence into that thing. And in fact, this idea of a central registry of experiments has already been put into effect in some fields. So in medicine, it's now starting to be used, although it's not very strictly regulated. So there are plenty of people who are not abiding by those kinds of regulations. And so it's a work in progress whether we can get past this issue with p-values. Well, I think that's about all I had to say about p-values for today. I hope that was useful. Go back and have a look again. There's a lot of details in here. Be sure to be looking at the reading again and see how it's talked about, see some more specific examples that you can work through.